All right, welcome to Friday lecture, everyone. Some announcements for today. Homework 4 will be released today and will be due next Thursday. As usual, 5 bonus points if you turn in a day early by next Wednesday. And in addition, the other thing going on is we have the first of 3 projects will be released later today. So the project is a longer assignment. You could think of it like an extended homework where we work through a case study of doing data analysis using the techniques you've been learning so far. You can work on the project on your own or in a team of up to 2 with one other person from the same lab. You can only work with a project partner from the same lab as you. You can't work with someone else in a different lab. This is going to be a 2-week project. You'll work on it in lab next week. In lab next week, you'll work on the project. We'll have a checkpoint that's due the 24th, and then the whole project will be due October 1st. Okay, so you'll have both a project and a homework, but we give you lab time to work on the project next week. All right, hopefully it's fun. I hope you get to enjoy applying what you've been learning to a more intricate data set. What we're going to do today is we're going to look at making predictions from data. So far, we've been looking at exploratory data analysis, just getting a sense of what's there in the data. We're going to start to look today at how to make predictions for the future based on historical data from the past. We're also going to learn a little bit more about table operations. We're going to learn how to use the group operation, what that does. That's a way of aggregating data. We're going to learn about pivots, and we're going to learn about lists. All right, so I want to start by looking at prediction. So let's jump straight to our demo notebook. And here we're going to work with a historical data set of measured of a bunch of families, almost 1,000 families. And for each family, what we have recorded here is some heights of the people in the family. So we have the height of the father, the height of the mother, and then for each child, we have the height of that child after they grew up to their full height. Okay, so this data set was collected out of interest in seeing whether we could predict how tall your children or the children of any couple would be based on how tall the parents were.
Professor David, a couple of questions about people not being able to see the numbers on the screen because they're fuzzy.
Well,
maybe
okay.
A little bigger, maybe? I can read them. Yeah, guys, is that better?
Very blurry. And a box covering them. Box covering the numbers.
There's a box covering the sort of bottom left of the screen.
Yeah, as long as it's not covering the numbers, hopefully that'll be okay.
It's covering the notebook, portion of the notebook.
Okay. Well, that's sad. Are we still covering the notebook? Yes, still covering the notebook. Is the notebook visible now? All right. Professor Nee, could you let me know if there's anyone in the chat who's reporting any issues with things not being visible?
Still issues.
Still issues. All
Yeah,
right.
there's a very pesky small gray rectangle at the bottom left corner.
Well, that's exciting.
And they're correctly saying that you can see most of the notebook, but there's going to be some moment that it covers the code that you're typing.
Well, that's no good. This gray box is still there. Thought I got rid of it.
Still there. There was the one.
All right.
There you go.
Very good. We'll do it a new way. No. So sorry about this, everyone. We'll figure this out. I thought I had a system. I tested it. But my tests were not conclusive. How about now?
This is wonderful. Thank you.
Okay, thank you so much for putting up with this. All right, so here we have this data set. The purpose of this data set, well, what we're going to use it for is we're going to see if you can predict the height of children based on the height of the parents. So for instance, if you have a pair of really tall parents, does that mean their children are going to be really tall too? So let's work out how we could figure that out. So what I'm going to do is I'm going to augment this table with another column that's going to be our prediction for how tall the child is. Now, if you have two tall parents, you might predict that the child will be tall. If you have two short parents, you might predict the child will be short. But if you have a tall and a short parent, maybe you predict the child will be somewhere in the middle. That seems like it would be a reasonable prediction. So what would you suggest if I told you the height of the father and the height of the mother? How would you come up with a prediction for the height of the child? Average. Yeah, the average sounds like a good attempt. Let's take the average of the father's height and the mother's height and use that as our best guess, best attempt at predicting the height of the child. Okay, so we're going to add a new column here that has the average of the father and the mother added as a new column here. So the way we can do that with array operations. You can see that in every row, we're doing the same thing. Whenever you want to do the same thing on every row, you should be suspicious that maybe a really good way to do that is to convert these into arrays and then do an operation. So we're going to get an array with the heights of the father, and we're going to get an array with the heights of the mother. And then the average of that is the sum of those divided by 2. Okay, so now we've got an array with the average height of the parents, which we can use as a reasonable, you might think of, way to predict the height of the child. So here's this massive array. Okay, so for the almost 1,000 families. So what we're going to now do is we're going to add this to our table. In fact, that table had a whole bunch of stuff that I don't really need. So I'm going to make a new table here with just some stuff that I care about. So I'm going to include the average of the parent heights as one column. Another column is going to be the height of the child. So I take the data from the original table with the height of the children. And for reasons I'll come back to later, I want to preserve the gender of the child. So now I've made a new table here with just the stuff that I care about and augmented with this average of the parent heights. Now, I want to explore the relationship between the parent average height and the child's height. So what would be a good visualization to help me explore the relationship between these two variables? A scatter plot, yeah. These are two numerical variables. When you want to look at the relationship between two numerical variables, a scatter plot is a reasonable way to do that. So let's do a scatter plot. And if I could type correctly, well, let me show you what to do when you get an error like this. Here I got an error and it gave me an error message, name error, name height is not defined. So it's telling me there's something wrong with this right here. And if you look up here, actually the name of my table was heights, not height. So I didn't type right. So let's fix the typo. And here is our scatter plot showing on the x-axis the parent average, the y-axis the child's height, and each dot represents a kid in this table. So what do you think? Do you think there's an association between this parent average height and the child height? Slight positive association. I would agree with that. I would have a similar reaction. It looks like it's kind of trending up and to the right a little bit. It's not super strong. Okay, so when we have an association, that suggests that one of these variables might be useful for helping us predict the other. If we knew one of them, it might help us predict the other. See, in this data set, this is a historical data set. So we could capture the height of the child after the child has grown to their full height. But maybe you got a pair of parents who have a new baby kid and they're wondering how tall their kid will be. Well, that's a prediction about the future. We can't measure how tall that kid will be yet. We just have to make our best estimate. All right, so what we can do is we can use historical data to try to help us make that prediction. So there's a weak association here, but you can see it's not a diagonal line. So the parent average is not necessarily determine how tall the kid's going to be. And there's no, it's not necessarily that the height of the kid will be exactly the average height of the parents. It might be a weaker association than that. So if I wanted to make a prediction about a new baby, maybe a reasonable way to do that would be to look at this historical data set at other babies whose parents had a similar height. Okay, so let's do that. Let's imagine here that we have a baby, a single baby whose parents' average height is 68 inches. And we wanted to make a guess about how tall that child will grow up to be. I think a reasonable way to do that would be to look at other babies whose parents' height was similar to 68, maybe 67, 68, 69, and check how tall their kids eventually grew to be. And that should help us predict how tall this new baby will eventually grow to be. Okay, so you can see all the dots between these two red lines are kids that were born to parents whose average height was close to 68. So there's a whole bunch of variability here. Some of these kids grew up pretty tall, 75 inches. Wow, that's like 6'3", I think. And some of them were shorter, like maybe 60 inches. That's like 5 feet tall. So there's a whole range. Given all these data points, how do you think you could summarize all of them to get a single number that's your best estimate for how tall a new kid would be? Yeah, taking the average of all these child heights sounds like a good way to get a value that's kind of in the middle of this. And so kind of our best estimate of what the height of this new baby might be. So how do we do that, compute that average? How do we make this prediction for a couple whose parent average height is 68 inches. Well, let's look in the historical data set and find all the other couples whose average height was close to that. Let's say between 67.5 and 68.5 inches. Let's make that new data set. That's the new data set of families of kids that are within that red bar. And then we're going to take the all of the heights of those children in this historical data. And that gives me an array with of numbers, one element for each child, and the number is the height of the child. And then I wanted the average of that. So let's take the average of that. And that's the mean height of children of from similar couples. And let's look at what that mean is. And that in this case, it's 67.62. So that would be a reasonable prediction for the height of a baby to a couple whose average height is 68 inches. So you can see that prediction was not exactly 68. Our best prediction is not actually that the child will be the same height as the average of the parents, but the average height of the parents helped us make a better prediction. So if I visualize that, if I display that on this plot, then my prediction is this red dot. Now, my prediction might be too high or might be too low because there's variability in how tall children turn out to be. It's not completely determined by the height of the parents, but this is my best effort. It's something kind of right in the center of where I think a range of reasonable values might be. So I did that for one baby, one couple. Now let's work out how to make predictions in general. So maybe I might imagine that I'm offering a consulting service to couples to make a prediction for how tall their kid is likely to be. So I'm going to write a function that will, given the height, the average height of the parents, make a prediction about how tall we predict the kid to be. Well, I already showed how to do that. It was this code. So what I'm going to do now is I'm going to copy paste that chunk of code, but I now want to generalize this. I might want to use this on a couple whose average height is not 68. Maybe it's something else. So I'm generalizing. This is the part that I expect to tweak is the average height of the parents. And I'm going to replace 68 with, in this case, some parameter h that I'll specify later. So what I did was I chose historical couples whose height was within a ½ an inch of h. And then this function computes the mean, computes the prediction for similar couples, and then we want to return that. The result of this function, the final prediction is that mean. So I need to add a return statement. So I'm showing you here how to take code that you might want to reuse multiple times, put it in a function. So now I can make a prediction for that couple before who had a parent average height of 68. There's that same prediction we got before, 67.62, same prediction. I made a function to do it for me, but I could now do this for other couples. Like what if the couple had an average height of 70 inches? They were a little taller. Well, you can see here, you expect your prediction for the kid to be a little higher, but not all the way up to 70. And what if you had a couple that was really tall? Their average height was 73 inches. That's over 6 feet. Then our prediction for the kid's height would be 70 inches. Okay, so higher still, but not as high as the average parent height. So what we're seeing here is how what our prediction for the kid's height depends on the heights of the parents. All right, so let me pause to take questions. I see comments here. Yeah, if the parents' heights are out of the range of historical data, can we still predict the baby height? Nope. If you got a pair of professional basketball players and you had no one in your data set that was at all similar, then this procedure isn't going to be very helpful. Well, let's come back to that one. Thank you, Dylan. We'll save your question there for a little bit later. You've got a great insight, and I'll come back to that one. So save that. You're right. Height of the parents is not the only thing that influences the height of the kid. There's many factors. Gender of the kid is also a very important one, and we'll come back to that one. All right, so we've been looking at how to make predictions for different couples. Maybe it's interesting to plot this. We've got a couple of sample numbers here, but you might start wondering, how does the predicted height of the kid depend on the height of the parents? So let's make a plot. What we're going to do is we're going to add another column to this table that has predictions for a bunch of couple heights. Okay, so let's for every row in this table, so for every couple in this table, let's look at what the average height of those parents were and apply our predict function to that to see what we would have predicted with this procedure for their kid. We would have predicted about how tall their kid would be. And then we're going to compare what we would have predicted to how things actually turned out. So I'm going to add a column to this table that shows what we would have predicted. So now I've got a table that shows how tall the child actually turned out to be, and then what we would have predicted based on the height of the parents if we'd used this procedure. So you can compare. Doesn't predict need a parameter value? Predict takes one parameter. You're right. You can see that predict requires one parameter. So where does that parameter come from? When we use apply, what apply does is it calls predict on every number in this table within the column that's specified here. So what we did when we did apply was we ran predict once for each row in this table, and the parameter we called it with was the number that came from this parent average column. Okay, so this prediction is the result of the prediction we would have made for a couple whose parent average height was 72.75. Okay, so now let's look at our predictions. Let's look to see how our predictions depend on the height of the parents. And maybe we can also compare that to how things actually turned out for these historical couples, since we have that data too. So I'm going to make a scatter plot. And here's my scatter plot. So you can see the blue dots are the data set I already showed you before. That's how tall the child eventually turned out to be after they grew to their full height. And the yellow dots is the prediction we would have made when that baby was born based on the parent heights alone. So you can see this yellow line we kind of call a prediction line. This is the graph of the predictions that we would have made based on the value on the x-axis. Okay. One thing you might notice, it might remind you of a regression line if you've seen that before, and we'll get to that later in this class. One thing you might notice that's kind of interesting is it's upward sloping. So the taller the parents are, the taller your prediction of the child is. That kind of makes sense. That seems reasonable. Another thing you might notice is this is not a diagonal line. What's the slope of this line? I don't know what it is, but it's not 1. You can see that the difference between parents of height 70 versus 64 inches, that's a 6-inch difference in the height of the parents. That leads to maybe I don't know, 4 or 5-inch difference in the height of the kids. Height of this yellow versus the height of this yellow. So like if your parents were 6 inches taller, then the kid would be expected to be about 4 or 5 inches taller. What does that tell you about how strong a relationship there is between the height of the parents and the height of the kids? Would you call that a really strong association or a weak association, or is there a strong influence there? Okay. I didn't really have a right answer in mind. Yeah, I think I could understand saying there's a weak association between, because even those children grown to the same, couples of the same height, there's a lot of variation that's not accounted for by the height of the parent. But you can also see that the parent's height has a fairly big influence. 6-inch taller parents gets you 4 or 5-inch taller kid. That's fairly large. Okay. So this lets us quantify that. Now, the next question you might wonder about as you start to see how, what kind of predictions we're making, and you look at these yellow dots and these blue dots, you might wonder, how accurate is this prediction? Okay, so we came up with a method to predict the height of a child. We're not going to get it exactly right. There'll be some error, but how large are these errors typically? All right, so let's see if we can get a sense of how large these errors are. So let me, what I'm going to do, the error is the gap between the yellow dot and a blue dot. So for a particular kid is some blue dot, like maybe this blue dot right here. The error in our prediction is the difference between the actual height that kid turned out to be versus what we predicted. So that's the difference between the height of the blue dot and the height of the yellow dot. In this case, that's maybe 5-ish inches error. Our prediction was 5 inches too low. Okay, so we can find the error as a difference between these two values. It's the difference between predicted minus actual. So I'm going to want to do compute the error for every row in this table. So when I want to do something for every row in the table, a natural thing to think of is arrays. And apply is really useful here because I'm going to apply a function to every row in the table. So you see here in this table, I have the actual and I have the prediction. So let's take the difference between the prediction and the actual for every row. When you want to do something to every row of the table, apply is a useful operation. So we're going to use apply here. We're going to apply, and the function we're going to apply is, let's take the difference between these two columns, and this difference function needs 2 parameters. So we need to specify the 2 columns, the column where we get the X parameter from, that'll be our prediction column, and the column where we get the Y parameter from, that'll be the child column. And then this is going to give, take the difference between those two values for every row. Okay, so that will give us an array with 1 element per row in the table. So let's now add that to the table. If I have an array and I want to add that as a new column to the table, I can do that as with column operation. And we're going to call that that column errors. I'm going to save this new table with the extra column. And you can now see here in this column, this has the prediction error, the error in the prediction we would have made. Okay, so you can see some of these are positive and some of these are negative. Some of them were too high and some were too low. And as you start to look at these numbers, you can start to get a sense for what the typical error is. It's common to be off by 2 or 3 or 4 inches, but it looks like it might be kind of rare to be off by kind of 10 inches. Well, let's try to get a better sense for how large or how small these errors are by doing a visualization. So what would be a reasonable visualization of the data in this errors column? What kind of plot or chart? Histogram. Yeah, this is one variable we want to visualize, and it's numerical. So a histogram is a good way to visualize the distribution of a numerical variable. Let's look at the histogram of that column. And if we do, we get a histogram that looks like this. So this shows you how large an error we typically have in our prediction, the error might range, and it might be very large, but most commonly it's somewhere between, at most off by 3 or 4 or 5 inches. Okay. So not too bad, not super precise a prediction. It's doing something. Now, someone asked earlier, what about the effect of gender? And you're right on. You're right on. You see, men on average grow up to be taller than women. So let's look at the distribution of errors. But now I want to look separately at the distribution of errors for men, and I want to look at the distribution of errors for women separately. Okay, so the histogram operation has an optional parameter that you can pass, which is called group. And if you specify the group parameter, then it will split up the data set into groups. And the way it splits them up into groups is based on the value of in some column. So if that should be a categorical variable, and it will have one group for each value of that categorical variable. So in this case, the column we care about, the categorical variable we care about is gender. All right, so you can see here that we have in blue, we have the errors for the females, the women, and for yellow, we have the error for the men. And what this is showing you is that the error for females is often positive, meaning that our prediction was too high. And the error for the males is often negative, meaning that our prediction is often too low. So if you knew both the height of the parents and the gender of the baby, then you could maybe there's an opportunity to get a better prediction. So maybe take a moment to think about that. If you wanted to make a smarter prediction, try to make a more accurate prediction by taking into account the gender of the baby, how could you do that? How would you go about that? What modifications would you make to the method? And if we did that, would you have smaller errors? Yeah, what do you think? Maybe type in chat your thoughts on how you might take that into account. Cool. Cool. Okay, I see a bunch of interesting and thoughtful ideas here. I like it. So one idea I see here is that maybe the height of male kids is best predicted by the height of the father, or maybe the height of the father is more important. So maybe you do a weighted average where you upweight the height of the same-sex parent. That's an interesting idea. That could be interesting to explore. I think that's a sensible thing to try. And a different suggestion I'm seeing, which I also think is really interesting, which is we could separate out in this data set by female kids and male kids. And then when we make our predictions, use one or the other of those smaller data sets. Okay, so let's try out that second idea. I think that second idea is very intuitive. We made a prediction by looking at similar couples from our historical data set. Maybe the notion of similarity should have been based not only on having a similar parent height, but also having a same gender baby. Okay, so that's what we're going to do, is we're going to narrow down our definition of who in the historical data set is considered similar. And I apologize for the massive scrolling here. What I'm going to do is I'm going to copy paste from the code I had before for making a prediction. I'm going to just make a small modification to that, which is instead of using all historical couples of about the same height, we'll only use the ones where the child also had the same gender. Okay. So here, the additional change that I need to make is I need to select the subset here where the gender is matches that of this baby. And now do my calculation of the mean using only those historical couples. You're right. Thank you. There was a bug in my code. Okay. So now we can make a prediction. For instance, the same couple whose average height was 68, if they had a female baby, the predicted height of that kid will be 65 inches. If they have a male baby, the predicted height is 70 inches. So a fairly substantial difference. Okay, so let's now do the same analysis we were doing before to look at the errors in these predictions when we take into account the gender of the baby. So we're going to make a bunch of predictions. And then well, make a bunch of predictions, and then we're going to add column, show this better prediction. We're going to compute the prediction errors just like we did before. So doing the same thing I did before to get the predictions and to get the errors, but now I'm using this new prediction method. And I can get a histogram of the errors in this new smarter method. Same thing I did before. I'm going to group this by the gender of the baby. And here you can see the histogram. So now we can see two things happen here. First, both of those distributions are centered around 0. So our predictions are no longer systematically too high or systematically too low. And the second thing that happened is, if we look, this histogram got a little bit skinnier. It kind of came together a little more concentrated and crowded around 0. Now the typical prediction error might be about plus or minus 3 or so, but it's rare for it to be much larger than, let's say, 3 or 4. So the prediction errors are typically a bit lower than they were before. And I can just show you a compare. Keep this one in your mind. Look at the shape of this histogram and see that it's very rare to have anything that's out here. And then let's look at our previous histogram and see, you can see here, there's a lot more that are out to plus or minus 5 errors, 5 inches error. Okay, so this kind of makes intuitive sense. If we have extra information, we could take advantage of that information to make a better, more accurate prediction. Error decreased, right on. Okay, that's prediction. You can see how you can use data to make predictions about the future. Take a little pause here, and then I'm going to start to show you some additional table operations that are handy. The first operation that I want to show you is called group. And group is useful when you want to summarize data, like compute the mean of the data or something like that. But you want to break down the data into a bunch of categories and get the mean of the data points in each category. All right, so the group operation is an operation on tables. You pick a column to group by. That's some categorical variable like gender. The group operation will separate them out by the value of that column. All the ones with the same value go together in the same group. And then for each group, it will compute some summary of the data in that group. So it might be the average of the values in that group, or it might be the number of rows that are in that group, or it might be the sum of all of the numbers that are in that group. Okay, so the first argument will be which column you use to split them up into groups. And the second argument will be how to summarize all the rows in that group with like a single number or something. Okay, so that second argument is a function that does the summarization for you. So let's see it in action. Here's a very simple toy table of ice cream cones that we've seen before. That's very small, so it can help us illustrate what we can do here. So suppose we wanted to group this by flavor. Split these rows up into, put together all the ones where the flavor is strawberry, all the ones where the flavor is chocolate, and all the ones where the flavor is bubble gum. All right, so we can call the group operation, tell it to group them by flavor. And what it will do by default, if I don't specify a particular way to summarize each group, is it will give me a count. It will count how many rows are in each group. So it says there was 1 ice cream cone in the bubblegum group, there were 3 in the chocolate group, and 2 in the strawberry group. So you can think of this as finding all the unique values of flavor and then counting how many times each occurred in the table. So that's the basic way of using group, where I want to summarize a group by how many rows are in that group. Sometimes I might want to summarize it in some other way. So for instance, let's imagine that I want to group them by flavor. And what I care about is the prices of the ones of the prices of the cones in each group. So I'm going to ignore the color. So let's just drop the color because I don't care about that for this purpose. What I want to do is I want to group it by flavor. And then the way I want you to, I'm asking Python to summarize all of the ice cream cones in a group is by taking the average. In this case, it's going to be the average of the price. All right, so now we can see that it computed me the results, but instead of showing me the count of how many are in each group, it showed me the average price of the ones in that group. So we can see the average price of the chocolate cones is a little higher, if that was somehow valuable to know. I could instead have focused on maybe summarizing all the cones in a group based on instead of the average price, maybe I want to know the cheapest ice cream cone for each flavor. Well, I could do that too. Here I use a different function for summarizing. So before I used the np.average function. And what the group operator did was it took all of the prices of the cones in that group, put them in an array, and then it called this function on it, the average function. Well, a different function you could use would be the min function. That would summarize all of the prices in the group by taking the lowest price. And so that shows me that if I really want chocolate, the cheapest chocolate cone I can get costs $4.75. But if I'm willing to put up with strawberry ick, I can get a cheaper ice cream cone with a strawberry flavor. That'll only cost, there's one that's as cheap as $3.55. You could use any other function you wanted instead of average or min to summarize all of these values into a single number. You could define your own function that summarizes a bunch of numbers in an array and some returns a single number to summarize them. And that's what the group operator would then use to come up with this value here if you passed your function as the second one. How does the library determine how to name the second column? The name of this column is based on the name of the original column where the data came from, price, and then it adds the name of the function that you were using to summarize all the data. All right. If my table had a whole bunch of columns and I did the group with an average, it would give me a whole bunch of columns here with a summary, the average of each one of those. So we'll see that in a moment. What would happen if I didn't drop that, that color column? Well, this is the great thing about having notebooks, that you can go to our course website, click on the demos for today, open up a notebook like this, create a new cell and try it and see what happens. So let's do it together, but this is something you could totally do on your own. And I want you to feel comfortable doing that. You won't mess things up for anyone else. Suppose we tried the same thing, but we didn't drop. Let's see, take the average, didn't drop. Well, now it would try to take the average of all the colors within that group and put that here, and the average of all the prices within that group and put that here. But what is the average of a bunch of colors? I don't know. So it gives you nothing useful. Okay. So average is only useful on numbers, and the color was not a number, so it didn't give you anything useful. All right, so here's an example of where this is useful. We could look at the welcome survey that you all filled out. And this survey has a bunch of questions in there. And one of the questions was about how extroverted do you consider yourself on a scale from 1 to 10. And so let's look and see what happens if we look at this data, but group it by your response to the extroversion question. What we find here when we do this group operation is that of everyone who said their extroversion level is 1, meaning it's super introverted, the number of people they text each day on average was about 3.3. And the number of hours they sleep on average was about 6.45. And so forth. So that's kind of interesting. This lets you look at the relationship between people's responses to the extroversion question and the responses to how many people they text. So let's plot that. Let's see. Let's take just the two columns with the extroversion and the average number of people they text each day, and plot that. And here is a plot where the x-axis shows people's responses to the extroversion question, and the y-axis shows the average number of people in that group texted each day. And this is fascinating, I think, because it suggests that those of you who consider yourself hardcore introverts text many fewer people, and those of you who consider yourself hardcore extroverts text many more people each day, which is kind of an interesting natural relationship. Let's do the same thing, but now let's look, instead of how many people you text each day, let's look at the relationship between extroversion for people in data 8 and the number of hours of sleep they get. Now I have a plot here that suggests that you all get that no matter what you answer to this extroversion question, in each group, people are answering on average about 7 hours of sleep. There's a little bit of variation. The very extroverted people are reporting maybe 7.04 hours of sleep, and the more introverted people are reporting, something else, except for those of you who answered one, super introverted on this question. There, the number of hours they get looks like many fewer, 6.5 hours of sleep. So if you're super introvert, do you sleep less? Well, this is a possible pattern, an interesting pattern that might be present in the data. So here we're doing exploratory analysis. We're finding some trends that might be present, but be careful, be wary about drawing a conclusion here, because if you look, there's also very few people who rated their extroversion level as 1. So it might just be that we have a very small sample size, and maybe there's no relationship between extroversion and number of hours of sleep. And later in this class, we will talk about when you spot a possible trend like this, how to get some evidence for whether it's real or maybe not. So let's stop there. I hope you have a great weekend, and we will see you in lecture on Monday. Thank you all.